Okay, I'm back, and in Unit 1, we talked about the atom, and we said that the number one thing that determined the identity of an atom was its number of protons. So hydrogen has one proton. Every hydrogen in the known universe has one proton. And then every helium in the known universe is going to have two protons. But we never said anything about the neutrons. So let's talk about ordinary hydrogen. So if you were just to grab some air and you look for some hydrogen in there, the hydrogens that you would find would consist of one proton and one electron in orbit around it. So we call that ordinary hydrogen. And 99.9% of the time, if you grab some hydrogen, that's what it's going to be. Okay, but there is a more rare isotope of hydrogen. And it consists of one proton, because all hydrogens are composed of one proton, and one neutron. And we're going to call that deuterium. And so it's more rare than what ordinary hydrogen is. And even rarer than deuterium is going to be called tritium. Tri means three. So tritium has three particles in its nucleus, one proton, because it's hydrogen, and then it's got two neutrons for a grand total of three. So all three of those are going to be called isotopes of hydrogen. Okay, now let's pretend that you had, we know that water is H2O. So H2O. So water is composed of two hydrogens and then one oxygen. So let's assume that we have two glasses of water. And one glass of water, the hydrogens in the water is ordinary hydrogen. And then in the other glass, it's going to have water that's composed of hydrogens that are deuterium. How could we tell the difference between these two glasses of water? I know, let's drink them. So let's drink each of the two glasses of water. How would they taste? They would taste identical because the chemical properties are going to be based on the electrons that are in orbit around those nucleuses. And so ordinary hydrogen and deuterium are going to have the same number of electrons, one electron. So chemically, isotopes are going to be the same. So how are they going to be different? Okay, one of them is going to be heavier because it's got two particles in its nucleus as composed to the other one, which only had one. So that means that the water that had the deuterium, we're going to call that heavy water because it has a heavy isotope inside of it. So that's how you could tell the difference between the two. Now, how are we going to name an isotope? Okay, nuclear physics people have a way of doing this. So they write down the symbol for the element. So in this case, the element that we're talking about is carbon. Okay, then we look at our periodic table of elements, and carbon has an atomic number of 6. It has 6 protons. So we put that number next to the C, and then we look to see how many neutrons does it have, and we add that to the number of protons. So the mass number is the number of protons plus the number of neutrons that are in that particular isotope. So you got two different isotopes of carbon. You got carbon 12 and you got carbon 14. So carbon 12 is going to have 6 protons and it's going to have 6 neutrons. And then carbon 14 is going to have 6 protons. And how do we figure out the number of neutrons? We're going to take 14 minus 6, which is going to be 8. So it'll have 8 neutrons in its isotope. So here's a sample question. How many protons and how many neutrons does this isotope have? So it's uranium-238. Now, you don't really need to write down that 92 underneath the 238. It's very useful to do that. But you don't have to write it down because everybody knows that uranium is 92 if you got your periodic table. So it's going to have 92 protons, that's its atomic number, and then we're going to take the 238 minus 92, and that's 146, and that's the number of neutrons that it's got. I also wanted to point out what are the numbers that have the decimals in the periodic table. So if you recall in unit number 1, we talked about the periodic table, and I said you only needed to look at the numbers that did not have decimal points. And those were the atomic numbers. That was all that we were really interested in unit 1. Well, now we can understand what the other set of numbers was in the periodic table, the numbers that did have the decimal points. And so what they represent is the averages of all the different isotopes. So do you remember that we said that ordinary hydrogen, 99.98% of all hydrogen is ordinary hydrogen. Okay, we're going to multiply that by the mass of a single proton, which is 1.0078, and it's called atomic mass units. Then we're going to add to that the deuteriums. So the deuteriums are more rare, so they're 0.0115% of hydrogens are going to be deuterium. And there's 2 of them though. And so it turns out that the mass of those 2 things in the nucleus is 2.0141 atomic mass units. And then the third one there, that's the tritium. So when we average all of those different isotopes together, you get 1.0079, and then that's the number in the periodic table that has the decimal point. Okay, now if you're in my astronomy class, don't worry about that, but I did want to show it to you. You'd use this extensively when you take a chemistry course, but we're not chemistry in here. Okay, we're going to take a break, and when we come back, we're going to talk about the forces that operate inside the nucleus of an atom.